Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of C++ Data Structures, we're going to be taking a look at max heaps. Now in the last video, we showed a basic implementation of a min-heap, and that was this heap structure, a binary heap, where we maintained two properties. One of them was an order property, and the other one was a shape property. Now for the min-heap, if we can remember that, right, so in a very simple example, we'd have something like this with a parent node, and then a child node that's left, and a child node that's right. And we just maintain the property that the parent node was going to be less than the left node or equal to, or less than or equal to the right node. Okay, so what's the difference between a max heap and a min heap, right? So we're maintaining the same shape property, meaning that we have to fill up all the nodes on a particular level before moving on to the next level, right? So we can't have a structure still that looks like this, right? So that's still illegal. Now, in terms of the order property, we're basically switching this around, right? So it's going to be now greater than or equal to the left node and greater than or equal to the right node. So what does this give us overall? Well, this gives us the property that the root node, or the very top parent node in our entire tree, is going to be the largest element in this entire data structure, right? So if we wanted some data structure where we've got very, very fast access to whatever the largest number is, well, we probably want a max heap. So let's see the small changes that we need to make to our min-heap example in order to implement a max heap, right? So this will be fairly simple. So likewise, we'll have the same calculations for parent, left, and right nodes, right? So we're still traversing the tree in the same way. What's really changing is our comparisons. So in this case, right? So right, the constructor is exactly the same, and we've got the exact same functions except renamed. Instead of extract min, it'll now be extract max. So for insertion, what changes here? So we're still going to insert a key at the very end to maintain that shape property, and then to so instead of here having fix the min heap property, we'll have fix the max heap property, and then our comparison will now be, instead of the heap of parent being greater than heap of I, right, we need to see if it's less than heap of I, right? Because we need to make sure we're switching only if the parent is a smaller number than the child, right? So again, this is inserting a node, say, at right? So if right is the new node that we're inserting, what we're doing is we're checking right against the parent, and we're seeing that if which one's bigger, right? If it's right's bigger, we need to switch these two nodes, and right will now become the parent. In the other case, right, for the min heap, it was the opposite, right? So we need to make sure that the parent node was smaller than or equal to the left and right node. So we had the opposite comparison there, right? And so then we have our heapify function and our extract max function that uses heapify. So again, with our extract max, the big difference here is, of course, we're calling heapify on the same element, the root node. So all of extract max actually stays the same, right? So we're just extracting whatever is going to be the root node, and we're calling heapify on the root node. And what heapify does, in this case, what we're doing is we're replacing whatever the root node is with the last node in the tree to maintain the shape property, right? And then we're maintaining the order property by, instead of comparing smallest, so if we go back, so let's actually open up our min-heap example real quick. So if we go ahead and open up, we'll go back to min-heap. If we go back down here to our min-heap heapify function, we see that we're finding the smallest element of the parent in the left and the right. But here inside of our max heap implementation, we're actually finding the largest number, right? And that's because the largest number, we want to keep that at the top of the tree, right? So just like over here on insertion, we insert something at the bottom of the tree and it bubbles up in this while loop. The same thing will happen with this heapify function. If the number that we took from the bottom of the tree is actually smaller, right? We want that to trickle down this time. So we'll compare it against the left node and the right node, and we'll figure out which is the largest, right? So if it turns out that whatever I is, which is what we call heapify with, right? If it turns out that that's the largest, it just won't move, right? Because that means it obeys the heap order property. So that means that the current parent node is bigger than or is greater than or equal to the left node or the right node. Otherwise, right? So if largest is not equal to I, Then we'll swap it with whatever heap of I with whatever the largest is, and that might be the left node and it might be the right node, right? And then we call heap of I on largest as well, right? So this will help us make sure that everything's in the right place. So let's go ahead and compile this and see how it works with a little example. So we'll do G++, we'll set the standard equal to C++11, input file is max-heap.cpp, and our output file is of course max-heap. Let's go ahead and run this as well. So we'll run max-heap, and here we see we're inputting 15 elements, right? So 4 complete levels, right? So we see at the very top, after we've inserted all of our elements, we see that 93 is at the very top of the max-heap, meaning that we've obeyed one of the key properties, being the largest element is the root node. So the root node's 93, and we saw, just like with our min-heap example, that every path down the tree is in order. Not necessarily that the subtrees are ordered, but that every path is ordered, right? So if we go 93, 92, 86, 15, that all obeys that order property that the parent node is greater than or equal to the child node. All right, so we see that. We see the smaller numbers tend to all be at the very bottom of the tree. All right, so let's go ahead and do an example, and let's open up Max Heap again, and let's get rid of a node, right? And we'll print out again. So let's go ahead and print out a new line. That way we have a space that way we can see where we're making our changes at. All right. So let's go ahead and call extract max. So we'll say int max is equal to heap.extract max, right? And that will turn max into whatever the largest element is. In this case, if we just scroll up a little bit, we see that that'll be 93. So we're extracting 93 from our heap, right? And then we can go ahead and call heap dot, right, and print heap, and this will go ahead and print out our new heap, right? And then we'll go ahead and put in another new line character. That way we've got some space at the very bottom, right? So we can go ahead and compile this again. Now let's see how this looks. So we see that what we went ahead and did was we took 93 out, and then we had some shuffling going on down. So what would have happened is this 63, right? So after 93 gets removed, we fill that gap at the root node with whatever the last node added was. So in this case, it would have been 63. So 63 would have gone to the top, and we would have found the smallest, or rather the largest of 63, 92, and 90. So 92 would have been the largest, so we would have swapped those two, right? And so 63 would have moved down a level, and then we would have called heapify on that element, and we would have compared 63 with 86 and 83, right? And we would have found the largest of those elements. Now in that case, it would have been 86, so 86 moves up, as we can see here, between our removed element version and our just our full heap, our binary max heap, right? And then we see that 63 eventually settles here, right? Because in this last comparison, it'll compare 63 with 15 and 49, and 63 is already the largest, so when we call heapify on it, it doesn't actually move anything. Right, so that's the basics of a binary max heap, right? So very, very similar to our last example. If you want more details on binary heaps, check out that video. This video just really shows how we can take our existing code for something like a min-heap and port it fairly easily to something like a max heap. As always, all this code can be found at github.com/coffeebeforearch. So feel free to check out any of this stuff. So we're under C++ data structures right here, but we've got stuff on, an overall crash course on C++ here. GPU programming with CUDA over here, and a Python one as well, and many others, right? As you can see, there's 21 repositories here. So let's go ahead and go to C++ data structures, and then we'll go ahead and navigate, and we see that under data structures and heaps, we see we've got our max heap and our min heap here. So here's our max heap. Feel free to download this, play around with it, let me know if you have any questions. And as always, I'm Nick from Coffee Before Arch, and I hope you have a nice day.